Okay, so let me start by reminding you what we did last time. So last time we looked at the Ginsburg-Landau theory, which okay, we can write it. Okay, let's write F is the integral d dx. So we neglect time-dependent fluctuations. Write 1 over 2m minus I grad minus E star A psi squared. This is the derivative term, minus mu psi squared plus v naught over 2 psi to the fourth plus b squared over 8 pi, where this b is equal to the rotor of A. And we can also obtain the Ginsburg-Landau equations by taking delta F to delta A equal to 0 and delta F to delta psi star equal to 0 gives us what is known as the Ginsburg-Landau equations, GL equations. Okay? We talked about the boundary conditions one needs for these equations to be solved properly. And we also described, we also found a quantity known as the psi, which is the coherence length, which is 1 over the square root of 2m mu. Okay? And we also related the psi to lambda. We wrote that the lambda over psi squared, which is defined to be kappa squared. So let me remind you that lambda is this is the coherence length. So we had a coherence length is psi is 1 over square root of 2m mu. And as we will see today, this is indeed the length scale over which the superconducting order parameter varies. Okay? And we had the penetration depth. So this quantity we obtained from this equation. Okay, so we took this equation and we redefined everything in terms of dimensionless fields, and this length scale naturally emerged. And then I argued that this is going to be the length scale over which things will vary. And the penetration depth, this we obtained already 2 lectures ago when we were talking about the Anderson-Higgs mechanism. So this is a different length scale. This is the length scale over which magnetic fields decay in the sample. Okay, so lambda is equal to m v naught over 2 pi e star squared m okay mu Okay? And from these two you can see that there's this parameter which we call kappa squared. This is square root. Okay, so kappa is a parameter. Maybe I'll write it like this. Kappa is a parameter which is the ratio between lambda and psi. This is a very important parameter because it distinguishes between different types of superconductors. And this comes out to be the square root of m v naught divided by 2 pi e star squared. That's it. Okay, so this is known as kappa. Okay. Good. So now let's talk about the behavior of superconductors in magnetic field. Behavior in a magnetic field. Okay, so the first thing I want to point out, okay, so let me first talk about it phenomenologically, then we'll make this more concrete. When kappa is much larger than 1, okay, it means that the length scale over which lambda decays is much larger than the length scale over which the superconducting order parameter can heal itself. Okay? Now, lambda is basically the length scale over which currents, screening currents, have to evolve. And psi basically, so you can think of psi as you know, in the end, okay, you know what, in a second I'll show this concretely. It's I don't need to talk about it. Let me just mention that in this limit, okay, this is called the type 2 superconductor, and here we have a B penetrates in vortices. Okay, it's called the mixed state, mixed phase. Okay, why do you call it mixed? Because basically magnetic field and superconducting, which could be like normal with magnetic field and superconducting without magnetic field, kind of naturally want to mix. So it's kind of it's equivalent to Milky behavior. So if you look, for example, at systems that have negative, like two phases that have negative surface tension, then they tend to mix. This is the kind of physics you see when kappa is much larger than 1. When kappa is much smaller than 1, this is what we call type 1 superconductor. Then B is expelled by the Meissner effect. Okay, so let's focus on this one for a moment. Let's assume that kappa is indeed much smaller than 1. Okay, then, and let's consider, so let's assume we have a magnetic field. Okay, assume a magnetic field is applied. Then I argue that what we want to look at is not F, but a Legendre transform of F. So we define G to be F minus the integral d dr of H dot B. A magnetic field, okay, let me write this. a magnetic field H is applied. So you can think of B as the induction field, which is the actual magnetic field that you're going to measure, and H is the external magnetic field that I applied on the sample. 4 pi. Now, why is this the thermodynamic potential I want to consider in this case? Because let's assume there is no superconductivity. Okay, if there is no superconductivity, all of these terms are 0 and I only have this. Right? Then if I look at delta G to delta B, okay, I get from this term, I get B over 4 pi. And from this term, I get minus H over 4 pi. Okay? And this whole thing is equal to 0, so I get that B is equal to H. Okay? Which is what I expect if there is no superconductivity. Okay? So what this Legendre transform actually does, it just it fixes the minimum of the thermodynamic potential to be at the appropriate state, which is exactly what you did in statistical mechanics and thermodynamics. Every time you switch between fixed number of particles, fix that, fix this. This is the same thing. We want to fix the magnetic. Basically, we're fixing H to be a constant. Okay, this fixes H to be a constant, but B will change. B in some regions will be smaller because the superconductor strains, and in some other region it can be something different. It can be, for example, fine. Okay, good. So now let's compare two limits, or if you like, two ground states. So thus, in the superconducting state with B equal to 0. So let's assume we have a superconducting state with B equal to 0. We have superconducting state. Sorry, let's write it differently. Let's now assume a superconducting state, a uniform superconducting state with B equal to 0, right? We saw already that if there's a superconducting state, the magnetic field must be screened. Okay, so let's assume that we expel the magnetic field. Okay, then then what we're going to find is that G is going to be equal. We plug in here psi is equal to the square root of rho naught. This is the uniform solution, if you remember last time, which is equal to the square root of mu over V naught. Okay, so if we plug this in, we get, what do we get? So this guy is 0, this guy is 0, this guy we can neglect, and we just get this. So we get minus the integral d dx over mu squared over 2v naught. Okay? So this is, if you like, the energy density of the superconductor. and it comes with a negative. Sorry, it's a negative energy because it basically gains energy from condensing, and this is the volume. So it's going to be volume times this energy. Now, on the other hand, if psi is equal to 0 and B is equal to H is uniform, then we have, let's call this G superconducting, and then we can have G normal in this case is going to be minus. So you see, then this guy becomes h squared over 4 pi, and this guy becomes h squared over 8 pi. So we get the integral over d dx h squared over 8 pi. Okay, so this is again volume times the condensation energy. Here this is the volume times the magnetic field energy. So what we conclude in this case is that if H is greater than, what do we have here? So this is, so I equate, okay, so sorry, so let's write it. So if mu squared over 2v naught is equal to h squared over 8 pi, this with this goes and this becomes 4, then I have h critical, which I'll explain in a moment what I mean by that, is 4 pi mu squared over v naught square root. Okay? What this implies is that when h is smaller than hc, then you gain more energy from screening out the magnetic field and having the magnetic field equal to 0. When h is larger than hc, then you prefer to destroy the superconducting state in order to enjoy the magnetic field energy. Okay? Or that's what minimizes the relevant thermodynamic potential, if you like. Okay, so the kind of physics that we get is basically this. So if I make a drawing of the magnetization M, as a function of H, okay, so B is equal to H, where's this? Let me make sure I don't, H, B is equal to plus 4 pi M. Okay, so this is this M here. So this M, I have here a straight line. And then we have here this HC. Then there's going to be a first order transition like this. This is type 1 behavior. And type 2 behavior, which we'll see in a moment, is different. It looks like this. And then we have here one thing which is called HC1 and another one which is HC2. So type 2 superconductors can basically withhold more magnetic field in them because they only break down, they don't break down at HC, they break down at HC2, which is bigger than HC, but they start to develop internal magnetization earlier when vortices begin to penetrate into the sample. So this is the phenomenology we want to describe. And now let's see.
Can you explain again? the differences?
Can I explain again the differences? So what I showed you here is that for type 1, right, let me write this. So this is type 2. Okay, so what I showed you here is that if we assume type 1 means that there is no magnetic field in the sample, okay? Then there is a critical threshold where basically we have two ground states. One which is normal without superconductor, or one which is superconductor without magnetic field. These are two local minima of the free energy. And what we see is that they cross each other, okay, as a function of the external magnetic field. And that happens exactly at HC. So this is a first order transition which occurs at HC. And you can see it in a jump in the magnetization.
So the black one is 0, then jump to the linear?
Yes. And but for type 2, it's going to be a continuous transition. And now let's try and describe that. So let me kind of portray how this thing works. So what we're going to do now is let's consider the following situation. So let's assume our coordinate system is this. This is x, this is y, and this is z. Okay? And we want to have a situation like this. This is x, where here we plot basically b of x. So b of x is changing from, and let's assume that h is equal to hc. So we're exactly going to park here in this limit in between. Okay? And then the magnetic field is basically, and here we have x equal to 0. So the magnetic field is going to go down here. And on the other hand, the superconducting order parameter is going to somehow superconducting order parameter is going to basically pick up here, and here if I plot psi of x, then this reaches square root of rho naught. Okay, somewhere deep in the sample. And what I want to do now is I want to compute the energy associated with this boundary. So the physics is that when this energy is positive, then the sample wants to develop as much interfaces as possible, and it will break down into as many boundaries as it can. And in principle, in that case, if it would be classical, completely classical physics, then it would break down into an, it would just completely collapse and mix. But this can't happen for a superconductor, because in order to take in a magnetic field, we will see that the order parameter needs to wind. And if the order parameter winds, then it has to quantize its winding. So there's a minimal, if you like, there is a minimal amount of flux that can penetrate. And therefore the magnetic field in the end has some minimal size or unit that it can mix in, and that's what happens here. It basically breaks into these vortices. And on the other hand, when the energy associated with this boundary is positive, it basically means it's kind of like oil and water. They don't like each other. They want to minimize as much as possible the surface between them, so they separate. They phase separate into regions, with large regions that are just magnetic field, and large regions that are just superconductor. Okay, so to see this, so let me write this formally. So what we assume is that b of x is equal to b of x is equal to b of x in the z direction, and therefore a of x is equal to a of x in the y direction. Okay, because now you know a is changing in the x direction and points in the y, so the rotor gives you a magnetic field in the z direction. Okay, and the psi of x, and this b of x is equal to hc when x goes to minus infinity and goes to 0 when x goes to infinity, and psi of x goes to square root of rho naught when x goes to infinity and goes to 0 when x goes to minus infinity. Or maybe I should switch, not to confuse you.
We are still working with London gauge, right?
Right now, let me see if the gauge is even important for me here. Yeah, you might be right. So the London gauge means that we, basically, okay. So the London gauge has to do with gradients of the phase, and yeah, here we're going to assume that the order parameter is real. Okay. So yeah, I guess essentially it is the London gauge. That's true. So just to remind you, the London gauge means that we choose a gauge such that the phase of the order parameter is constant everywhere, and therefore all the variations occurring in space are all shoved or absorbed into A. Okay? Questions up to now? Okay, so now, and what we're going to look at is, again, we're going to look at G, which is basically G over volume. Okay, so let's look at this quantity. Let's actually define G tilde, okay, which is G minus hc squared over 4 pi, okay? And G is basically this thermodynamic potential over the volume of the system. So what does this imply? So I remind you that at hc, basically this Gibbs free energy, it was, so, you know, G, I remind you that G is equal to hc squared over 4 pi minus, which is equal to minus mu squared over 2v naught. That's what we had before. So if I shift it by this, plus here, plus. Then basically what it tells us is that the G is, so I get here that the G tilde is equal to 0 and 0 when x goes to plus infinity and when x goes to minus infinity. And then something happens at x of order 1. Okay, something happens. And basically what's going to happen is that depending on kappa, we're going to see it's either going to become negative or positive near the boundary. it's 8 pi. 8, was it 8 pi? 8 pi. Probably you're right, 8 pi. Is that true? Yes, it's true. Okay, good. Okay, good. I need to fix this in the notes also. It's a mistake. Okay, then we can write our Ginzburg-Landau free energy in this case. And we get that G tilde is equal to 1 over L, the integral from minus L over 2 to L over 2 dx. 1 over 2m dx psi squared plus E star squared over 2m a squared times psi squared minus mu psi squared plus v naught over 2 psi to the fourth plus b minus hc squared over 8 pi. Okay, now what did I do here? So I remind you that A is pointing in the y direction, so it only appears in the derivative, it only shifts the derivative along y. But psi is not changing along y, so therefore it only appears in the squared form, like this. This is what they call the diamagnetic term. I don't know if you know this context, but basically if we have a coupling which is something like, if you have minus I grad minus EA times psi squared over 2m, then there are basically two types of coupling terms. One is the current coupling, right? Because the linear coupling, the terms that couple, maybe I'll write it. So it's this term basically implies I grad minus EA times psi star, right? This whole thing dot, right? Minus I grad minus EA acting on psi, right? This is what this thing says over 2m. So there are terms, so there's the gradient times the gradient, times psi, that's the gradient squared. Then there are mixed terms like this times the gradient times that, and this times that, right? This will give you the coupling to current, to the current operator. And this is what we call the power magnetic term, okay? And you notice that this coupling is linear. Okay, it's linear in A. So when we do, for example, linear response, we typically consider this term, or if you like, the coupling to photons at a certain frequency will be given by this term. And then there is the term where this times that, that's A squared. This is what you call the diamagnetic term. Okay, and yeah, there's a whole story behind this in linear response theory and what the different terms do, but I won't get into that. So in this case, we only have that, and in the derivative term, it's not modified because the derivative is along x. There is no ax, so it's not modified. And then these terms, you just saw them; they're trivial. And now we make a convenient definition. We define the coordinate space eta as let's define x as a lambda eta. So eta is a new coordinate that has no units. The units of length are now defined by lambda. Okay, we define a field f, which is square root rho naught. It's right. Psi is equal to square root rho naught f. So f is a new field again, it has no dimensions. Okay, and is measured in the density, square root of density of the condensate. Then this is a lambda hc times A. A is now the vector potential, which has again no units. And finally, B is the magnetic field, which is hc, B is equal to hc times B. So B is also a magnetic field that has no units. And when you plug this in here, you find that G tilde becomes the following. Becomes lambda over L, integral from minus L over 2 lambda to L over 2 lambda d eta. And then we have 2 over kappa squared df to d eta squared plus a squared f squared minus 2f squared plus f to the fourth plus d eta a minus 1 squared. And now we can look at the equations delta G tilde to delta F and delta G tilde to delta A equals to 0, and this gives us the equations F double prime equal kappa squared 1/2 A squared minus 1 times F plus F cubed. And here we have A double prime equals AF squared. So these are Ginzburg-Landau equations. So remember that for any Ginzburg-Landau free energy, we have the equivalent Ginzburg-Landau equations, which are simply given by taking functional derivative and equating to 0. These are basically the saddle point equations of this Ginzburg-Landau theory. Okay, and as you can see here, now I can erase these guys, right? And I can write here B of x is basically just 1, and f of x is 1 here. Okay, so if I write here f and I write here b, and this is 1 and this is 1, and everything's super convenient. Now to analyze this thing, we do a trick. There's a trick, a very useful trick, which is to notice so one can notice that these two equations can be summed up together in the following way. We can write d to d eta of 2 over kappa squared df to the eta squared plus 2 minus a squared f squared minus f to the fourth plus dA to the eta squared. This whole thing is equal to 0. Now why is this true? Because if you take, let's call this equation 1 and this equation 2. Basically, if you take this derivative, okay, you'll find that this equation is actually Okay, hold on. Let me rewrite. One moment. Let me just to explain to you where it comes from. From this equation, I can actually write f double prime over kappa squared minus 1/2 a squared minus 1f minus f cubed is equal to 0. Okay, so let me call this equation 1. And from this equation, I get that a squared minus af squared is equal to 0. And let me call this 2. Okay, so these are two equations that are basically 0. Both 1 and 2 are equal to 0. So it turns out that this equation is actually just 4 times f prime times 1 plus 2 times a prime 2. Okay, so you can just take these two equations, put them in here, and you can verify that you get the same thing. Now, why is this useful? Because this is a total derivative equals 0. It tells you that at the saddle point of these equations, okay, this, whatever sits in here, is a constant. Okay? Now, I want to argue that I even know what this constant is. How do I know what this constant is? Because let's imagine, you know that the a to the eta is basically b. Okay? The a to the eta is just b, this b over here. So, if I take this to minus infinity, this equation here, to minus infinity, the f is 0. You see f goes to 0. So I only have this term. And this term is just b squared, and b squared is 1. So you just get 1. So what I want to argue, basically, is that 2 over kappa squared d f double prime plus 2 minus a squared f squared minus f to the 4th plus a prime squared is equal to 1. This is basically the conclusion. Okay? So I know this is a constant, and I know that I can use that. How do I use that? What I'm going to do is I want to isolate f to the 4th here. So I write f to the 4th is equal to 2 over kappa squared f double prime minus 2 minus a squared f squared plus a prime squared minus 1. Okay? And this we can now plug in here. Okay? So I'm going to erase these. So imagine that I plug this in this f to the 4th here. Then I get that this g tilde guy is lambda over L. Oh, shit. By the way, this is not correct, of course, because we're missing units of energy density, which are given by mu squared over 2v naught. That's the basic energy scale. Or hc, if you like, you can write hc2 over 8 pi. Same thing. So mu squared over 2v naught. But I missed this on purpose. I was checking you and no one noticed. So I know that you're not listening, which is not surprising given the complexity of this expression. Basically what we find is the following thing. We find 4 over kappa squared df to the eta squared plus 2a prime minus 1. Okay, and now I can already argue that the surface tension is indeed positive and negative in the two limits. Okay, so the first result we already have here. How do we see this? So let's imagine that kappa is much smaller than 0. Smaller than 0. Kappa is much smaller than 1. Okay? Kappa is tiny. It means that this term is negligible and the energy is dominated by this term. Now this guy, this is always positive. So when kappa is much smaller than 0, the surface tension is positive. And in a moment we're going to compute it exactly. I'll show you why. Okay? In the other limit, when kappa goes to infinity, okay, then we're dominated by this term. Now let's look at what we have here. You see that b is varying between 1 at minus infinity and 0. This means that this term is indeed positive, a prime, but a prime minus 1 is always negative. So this term becomes negative. So it tells you that in the opposite limit, so we can conclude that G tilde is positive for kappa smaller than 1 and G tilde is negative for kappa greater than 1. So just to explain, and by the way, I want you to notice that this is energy density, but if we want the energy of the interface, then we multiply this, the energy density of the interface, we multiply this by L. Then we get something that even in the limit where L goes to infinity gives us a finite result, which is the energy density. And okay, so what is the physics? So imagine that you have a boundary, okay? Here you have a superconductor and here you have a normal state with a magnetic field. Okay? Now imagine that you create some sort of perturbation here, which enhances the surface between the two regimes. So once this is positive, if the energy is positive, then there is tension. It's like so you can have waves that propagate along this thing, but basically there is a force that is pushing back, trying to prevent this from happening. If the energy is negative, the opposite happens. The small perturbation is unstable. And then you start getting, basically you're going to get fingers that are going to penetrate in, and it looks like, bubbles start penetrating in, and you get mixture between the superconducting and magnetic field, and that's why they call this a mixed state.
Something like water boiling.
Well, the point with water boiling, the reason I don't want to agree with that is that actually a bubble of gassic water inside water has positive surface tension. And that's why the bubble has a finite size. Physically, what happens when something has a negative surface tension is you basically get mixture. You get something that would look milky. They just mix together completely. Yeah, what would be a nice example of that? But yeah, actually, it's just So, you know, that's what soap does. If you go home, to some extent, because there is some cutoff scale for this, but if you go home and you put oil and water together, you'll see they separate. That's this phase, the positive. Now add soap and mix it. What happens is that soap is exactly what you need in order to bond, you know, oil on one side and water on the other. And by that, it makes this surface tension, reduces it. Okay. And then it mixes, and you'll see that what you get is milk. You get something milky. And it's milky, of course, because of the refraction index, which is varying over many length scales, micron size, and so on and so forth. But yeah, it's not exactly. Bubbles are something else. Basically, you're just generating these bubbles at the bottom, and they have nowhere to go. They have to go up. Right. But yeah, the reason I'm imagining it here as bubbles is because we're going to see that actually you can't shrink these regions to zero. Because the point with when the surface tension is negative, you want to create as much surface as possible. So you want to make it porous. Basically you want to make the material look like a sponge, or you know, something that has as many surfaces as possible. But here there is going to be a minimal size for these bubbles, and these are vortices. We'll talk about that. But let's take a break now.
No time.
And come back. Question? Yes.
You can explain why G tilde smaller to 0 when K large?
Because when kappa, this is not case, kappa.
Kappa, yes.
When kappa is huge, this term is negligible, and we're controlled by this term.
But we have two terms. One positive and one negative.
Yeah, and the product of them is negative.
How we know?
What do you mean? This because
A is normalized?
no. I showed you. A prime is just B.
Okay.
Okay. Basically, here you have to remember that here I have a very sterile condition. I'm assuming, you know, only variations along X. You know, I'm just computing the energy of this object. They didn't say anything about it. You know, I'm not putting in perturbations. That makes everything complicated. Just asking, what is the energy of this infinite boundary, which is super straight and nice, and I just found that it's negative. So now I know that the system wants to create a lot of boundaries like this.
Okay. And what you did here with the drawing is the coexistence line between the two phases. There is no deformation, right?
In the calculation, there is no deformation, no. But we use this to, you know, one way to think about it is like, imagine that this is really a bubble and it really has curvature. And we just did a calculation, you know, very, very, in a small region close to the bubble. So the only thing that's really important for this is that the size of the bubble has to be much, much larger than lambda. Lambda is the typical length scale which we used in this calculation. Okay? אוקיי, אני רוצה את הביטוי, איזה ביטוי אני רוצה? אוקיי, so let us see. So let's continue. So I want to do two things. רגע, מתי אמרנו מזמן?
היינו אמורים להתחיל כבר, לא פשוט...
מה קרה?
עינת התעקה בחוץ. לא צריך לפתוח את הזה, אז...
שנחכה לה?
לא, תתחיל, כאילו... אני מקווה שמישהו יפתח את הדרך.
כן. יש שם מספיק...
כן.
קקות. קיצור... yeah, so let's continue, Nus. So I want to do two things. I want to look first at the limit of very small kappa. And the reason I want to do that is because there is a canonical solution, which I want you to see, you know. And the second limit is I want to show you that actually you see what happens is that basically, you know, if G tilde is negative for a very large kappa and is positive for very small kappa, there must be somewhere in between where it's 0, which is the boundary between the two. And I want to show you that that happens exactly at 1 over square root of 2. Okay?
1 over the square root.
Yeah, when kappa is 1 over square root of 2. That's the boundary. That's where g tilde is equal to 0. I think I want to keep this equation here. I guess I need this equation. I'm going to keep this equation, and I need this equation. So stop me if I... So let's start from the limit. Okay, so in this limit we have basically only this term, okay, so in this limit what happens, let me make a drawing for you. So basically yeah, looks like this. The magnetic, so let's assume this is x equal to 0, this is x. Okay, in this case, what happens is that this is A of x. It changes very, very rapidly. But on the other hand, f is going to do something much, much slower. Okay? Where this is a length scale, which we will see this is basically psi. Okay? This is the reason I wanted to show you this regime. Okay? So what this implies is that we can neglect variations of A. Okay? And we can focus, let's focus on this regime where we want to assume that psi or f can still be small. Sorry, not still be small. Maybe what I want to say is that there is a regime here where a is essentially 0 and we can solve only for f. And that means that we can neglect a in this equation. Okay? So what we have, basically, we can look at this equation here. I guess. Let me see if that's the equation I want.
Oh, psi is not constant.
Ah, shit. Okay, so I erased another. What?
Psi is not a constant. Fix or mu.
Psi is a constant. Yes. Ah, no, this is not psi. This is f. Oh, this is the scale.
Ah, okay.
So this is f of x. Okay. And this length scale is psi. We will see. We will see. Okay, but one step at a time. So the first thing I want to use is
what are we trying to do?
What are we trying to do? This is an excellent question. Why is this equation is wrong, by the way? How did this happen? No, yeah, this was squared. Okay? This is this, you see, this is this thing. It can't be f double prime. The derivative of this will give you the f double prime. What? What was the question? What are we trying to do? Okay, so again, let me explain. So we concluded the last lecture by saying that when kappa is much smaller than 1, we have a positive surface tension, and then we have phase separation. And when kappa is much larger than 0, we have negative surface tension, and we have mixed state. Now I want to look specifically, so I want to do two things. The first thing, I want to show you that in the limit kappa much smaller than 1, we get a canonical solution where the superconducting order parameter basically heals itself over a length scale psi, which in this case is going to be very long compared to, spatial variations lambda.
What does it mean, a canonical solution?
Well, it's just some solution which is very common, important, okay, which I want you to know. Okay, and the second thing I want to do is I want to show you that the transition between negative and positive behavior, or positive and negative behavior, happens exactly at kappa equal to 1 over square root of. But let's start from the first thing. So we're doing this. Now this changes. Now I want to focus on this regime, okay, where I can neglect A and A prime, because they're both 0 in that regime. Or can I assume that they're 0.
But negative A is 1.
What? No, I'm looking exactly here,
Okay.
in this regime. Okay? And in that regime, what I obtain, I obtain that 2 over kappa squared f prime squared plus 2f squared minus f to the 4th is equal to 1. Okay? So therefore, I find that f prime is equal to, so I get basically, so this, okay, let's do this a bit slower. So 2 over kappa squared, so this thing becomes f to the 4th minus 2f squared plus 1.
Shouldn't that 2 be a 4? 2b?
Why 4?
Because you said it's the same in this equation.
No. This is not. No. Okay, let me explain. In this, to move from this equation to this equation, we used this equation. We isolated f to the 4th and plugged it in. And then we obtained another 2 over kappa squared, which gave us this 4. Okay, that was the reason I said it's not double prime. I don't know how the double prime came in. I'm having a difficult day. Especially with all the kdichot שהיו פה קודם. Okay, so now we're focusing on the regime here where A is equal to 0. This is not A, by the way, this is A prime. But A prime, I assume that both A prime and A are 0 at positive x. I'm solving this equation. Blah, 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 blah. I write this thing. Now this thing you can see is basically just f squared minus 1 squared. Okay, or maybe better to write 1 minus f for a reason. Actually, it doesn't matter, of course. So this implies that f prime is equal to kappa over square root of 2, 1 minus f squared. By the way, this is squared here. Squared. You're not listening again. The solution of this equation you know, right?
Finch.
Close.
Kosh.
Tanch.
סתם
So this gives us f is equal to tangents hyperbolic of kappa eta over square root of 2. Okay? And if we plug in, we get that psi, plug in the, give it the units, then we get the corresponding psi is equal to square root of rho, tangents hyperbolic of, so remember that this eta is like x over lambda. Okay? And kappa is lambda over psi. So we get x over square root of psi, which is what we anticipate. So basically this shows you that this is basically a tangent hyperbolic changing or varying over a length scale psi. So psi is what we call the healing length. It's the length scale that takes for the order parameter to heal itself, to go back to its full value. Okay? It's a very, very important length scale. Good. And we can use this, in fact, to compute in this limit. You know, we can neglect this, plug this in here, and compute the energy. I'm not going to do it. It gives some number. It's not very important for me.
And only when psi heals itself, we get the condensation.
No,
No.
no. Everywhere where psi is finite, there is condensation. But there is a question whether it retained its full value or whether it's still healing.
But psi is always finite.
That's true. But that's, you know, a mathematician would say that psi is always finite. A physicist wouldn't say that. Right?
Why?
Because if, you know, if x is much smaller than, you know, if you go many xi's deep in here, it's essentially zero.
So you mean non-zero? Okay.
What? Ah, no, you know, zero is not a finite number.
Why?
So,
What do you mean, why? Zero is finite? In
Yes.
which, even in English, even in simple English, zero is not finite.
I have here zero balloons. It's a finite amount.
No, it's not. It's the opposite of infinity. It's not a finite number. It's the inverse of infinity. Okay, and now the last thing I want to do is to look at. Let's look at kappa equal to square root of 1 over. Sorry. Kappa is 1 over square root of what do I want to say? Okay, now let's look at the limit kappa is equal to 1 over square root of 2. Okay? So, in this case, I take this equation, okay, and I find that 4f prime squared plus 2 minus a squared times f squared minus f to the fourth plus a prime squared is equal to 1. So now let me move the 1 over here, so I get 4f prime squared minus a squared f squared equals on the other side. So let me move. So I'm moving this to the other side, that to the other side, and this guy to the other side. So I get 1 minus f squared minus a prime squared. Yeah. Now,
You're missing an F.
what? No. Which?
The okay.
Okay. Now let me see. Why did I want to do this?
A tag, it's the A to the eta.
Because we
What?
What is A tag? The A to the eta?
Yes.
instead of f prime, we can plug that solution, right?
Instead of f prime, we can. No, wait a second. I'll tell you in a moment what I want to do. Yeah, and I think I have another. Okay, I have another equation, which I erased. So I want to remind you. Let me write. So I had two additional equations. So I'm just copying. Where is this? So I had a double prime is equal to af squared, and f double, okay, this I don't need. So, but I had this equation, so okay, maybe I'll write just to remind you, and I had f double prime is equal to kappa squared 1/2 a squared minus 1f plus f cubed. Okay, so this, I'm just reminding you. But I want to focus on this equation for a moment. Why? Why do I want to focus
Yeah,
on
because if you plug both solutions, you get the equality.
I get what?
That one, like you get the result that they are equal. Okay.
Well, no, they're definitely equal. They're definitely equal because of this equation.
Right.
There is no, but what I want to argue is that they're actually equal to 0. And let me remind myself. I thought I got it before the lecture, but now suddenly it escaped me again. So basically one can show that these are 0, and I'll let me 1 second.
If you take a derivative of both sides, you will have elements of a double prime and f double prime, and you can play with that maybe.
Yeah, let me see.
Hold on. A and F.
One moment. Give me one more second. One more second. A double prime. Okay, I'll have to. Wait, f prime is minus 1/2 af. Okay, never mind. I'll have to remind me. Next lecture, I'll show you. So this question mark, one can show that this is equal to 0. If this is equal to 0, we can plug this in here and find that g tilde is equal to 0. But I don't want to waste time on this. It escaped me. But so next lecture I promise to fill in the gap. So basically, yeah, I thought I had this, but I don't right now, and I don't want to waste time. But the point is that when kappa is equal to 1 over square root of 1/2, g tilde is equal to exactly 0, which tells us that this is the boundary. So why is this important? This is important because, if you go and calculate the parameters of some Ginsburg-Landau theory for some superconductor, and you find that kappa is larger or smaller than 1 over the square root of 1 over square root of 2, that's exactly the limit where you should expect to see type 1 or type 2 behavior. Okay? Mm-hmm. Good. So now let's discuss HC1. So, let's discuss okay, sorry. So let me remind you. So we have the following phase diagram. So we have, if we look at the magnetization versus H, then we said we have HC. And if you have a type 1 superconductor, you basically have behavior like this. But if you have a type 2, then there's actually 2 additional fields, HC1 and HC2. And you basically have, this marks the point where they become equal. It's actually more curved, actually, like this. What we want to do is now understand these fields. Okay, and let's start from HC2. Okay, so the idea is
HC2 is HC for type 2.
It's so the point is that if you have a type 1 superconductor, we said there is an abrupt first order transition at HC between a superconductor which has 0 magnetic field in it and a normal state which the magnetic field penetrates. Mm-hmm. And for a type 2 superconductor, there is actually a transition. There are 2 transitions. One where you have Meissner. So this is Meissner. Meissner. Okay. Sorry, Meissner. And here you have mixed with vortices. Mm-hmm. Okay. And then you have normal.
Oh, okay.
So both of these are superconducting, but mm-hmm. they are distinguished whether you have vortices or you don't have vortices in the cell.
Mm-hmm. So this is second order phase transition?
Yes.
Yeah, to be honest, it looks second order in this sense, but it's kind of difficult for me to call it second order for other reasons. But yes, from this perspective, from the magnetization, there is no jump in the magnetization. Change is continuous. Because you have to understand that here it's still superconducting. So there are behaviors that look second order at this point, but it's not really a second order transition. Because I want to remind you that second order transitions, we are used to them happening when you break a symmetry. You remember when we talked about that? You spontaneously break a symmetry. Here there is no spontaneous symmetry for this, so it's much more delicate than that. But this is definitely first order, that's for sure. Okay, now okay, so now I want to look at these 2 fields. Okay, let's understand them. So let's start from the upper critical To be honest, there is actually a third magnetic field which is called HC3. Okay, there's a third magnetic field called HC3, which has to do with the breakdown of transport. So it turns out that there is a sorry, what am I talking about? there's a third magnetic field, which is called HC3, where you have surface superconductivity. Different. So this is HC2 is typically defined as a thermodynamic upper critical field, where the bulk of the superconductor becomes normal. Turns out that there is another threshold, even higher, where you have zero resistivity, which is all carried on the surface, and that's some. But typically they're the same, but they can be even separated by that. Okay, anyway, but let's talk about the upper critical field HC2. So the way we think about it is that we're going to write, our Ginzburg-Landau equation is 1 over 2m minus I grad minus EA, right, squared times psi. Okay, this thing is equal to mu psi minus V naught psi squared psi. This is the Ginzburg-Landau equation, where I just push the constant terms to the other side. Now, let's assume that the transition here is indeed continuous as a second order transition, as we were saying, where basically psi goes to zero continuously. Then it means that close to HC2, we can neglect this term. This is small. Okay, it's basically zero. Okay. Now let's choose a gauge such that A is equal to AX and BZ X in the Y direction. Okay? And BZ, this BZ, we will call it HC2, which you will understand in a moment why. Okay, so if I write it in this way, okay, then you see that what I have here is 1 over 2m dxx minus dxx psi plus e squared over 2m e squared bz times x squared psi is equal to mu psi, right? Questions?
Why is the x squared?
Here this is b squared. All right, this is b squared. I plug this in A.
It's BZ X Y hat.
Yeah, it's BZ because this is
I
A.
think it's cross.
No, it's A. It's A.
Okay.
A has to vary in order for there to be a constant magnetic field.
Okay.
Okay?
Is it orthogonal?
Who is orthogonal?
Yes.
This is in the y direction, and I'm basically assuming, okay, you're right. I'm basically assuming here that psi is a constant in the y direction and changing in the x direction. So basically I'm looking for a solution. Okay, let me explain to you what I'm doing. So I'm thinking about, this is like y, x, and z. I am looking for a solution that is going to be like a stripe, which is superconductor nucleating. Okay, but I'm assuming that it's nucleating like a stripe. I don't have to do it like that, but it's just easiest to do it like this. I can actually do, I can also do something like a small dot, and then I need to choose a different gauge, which is something like a symmetric gauge. So I can choose a symmetric gauge where A is something like minus b over 2 y in the x direction plus b over 2x in the y direction. Okay, and if you do that, you can transform this equation to polar coordinates, and then you will have a harmonic oscillator in 2 dimensions, which you can solve in polar coordinates with Bessel functions and like have fun. Okay, but actually you don't need to do Bessel functions. You can just do in Cartesian coordinates. You can have like it's like a parabolic potential in both directions, and you can solve it. But I'm not going to do that. I'm assuming that it nucleates like this. Okay, and when I write this thing, well, I've already told you, but does this look familiar to you?
Harmonic oscillator.
It's the equation of the harmonic oscillator, right? So I can rewrite this equation. I can rewrite this equation as minus dxx over 2m, psi, plus m omega squared over 2m psi equals to mu psi, where omega in this case, right, it's going to be E B. There is no 2m here over 2. It's EB over m, right? EB over m. Okay? Okay? Now, what does this equation tell us? Basically, remember that when mu, so I remind you that this mu here, mu is equal to alpha, t minus tc. So when t is smaller than tc, when t is smaller than tc, mu is, no, it's the other way around. It's tc minus t. Tc minus t.
Alpha is negative.
Yeah. No, alpha is not negative. No, so when mu is, when t is smaller than tc, then mu is positive, and we have a condensation, right? Which is rho naught is equal to mu over v naught. Okay? When when t is larger than tc, mu is negative, and we have only a single minimum at 0, and there is no condensation. Okay? So basically, when mu is equal to 0, that's exactly the transition point. That's where we find the first non-trivial solution of psi. But here what we see is that to get a non-trivial solution of psi, we need mu to be positive. At 0, there is no solution. The first solution occurs when omega over 2. This is the lowest solution, okay, when mu is equal to omega over 2. This is the first solution. And this gives us HC, because, why does it give us HC? Because what we get is that we have E squared B squared over 2m squared equals to mu Wait a second. Something here is not okay.
White square.
EB over M. Omega. Is this true? If I put here EB over M, I get E squared B squared over M squared. Oh, we need X squared. X squared psi. That I forgot. No, but it looks, everything looks okay. Let me make sure. This looks fine, yes. Omega over mu, when mu.
So it shouldn't be square.
I see. The square, that's the problem. I don't have any square. Yes, sorry. So I get that EB over M over 2M equals mu. Okay? So from here I get that the critical B, let's call it HC2, is equal to 2M mu divided by E. Is that true?
What is the physical meaning to omega? Are there oscillation there?
What?
Is there a physical meaning to omega? Is there something oscillating?
Yes, this is the cyclotron frequency. So when you put particles in a magnetic field, they oscillate at the cyclotron frequency. This is what is oscillate.
Like Rabi oscillation or
Like what?
Rabi?
No, it's not Rabi oscillation. It's much simpler. If you put a particle in a quantum particle in a magnetic field, so even if it's a classical particle, it's moving in a magnetic field, this is the cyclotron frequency. Okay? And but once you make it quantum, there is a minimal frequency, here in this case mu, which is omega over 2. And this gives us this upper critical field. Now I want to talk for a moment about this upper critical field, HC2. Okay? But something is still about, I know. Okay. So let us look at this expression for a moment. So I want to rewrite this using the fact that psi is equal to 1, psi squared is equal to 1 over 2m mu. This is this length scale psi. And also I want to remind you that up to now we took h bar equal to 1. Okay? So you agree with me that h is equal to 2 pi. Okay? So yeah, so I can add, so if I want to add these units, so here I should have had h bar squared, okay? And then this would be h bar, okay? So let me add this. So I basically have that hc2 is equal to h over e divided by 2 pi psi squared. This is what I have. Because h over 2 pi is h bar is equal to 1. Okay, so what do I have? This is a mess. I apologize. So let me write it here. So what we found is that HC2 is equal to phi naught over 2 pi psi squared. Okay? Which goes like 1 over we saw that xi squared is tc minus t. Okay, so
Why?
Isn't there a problem with the units?
sorry, it's not tc or it's tc minus t. What?
Isn't there a problem with the units?
Which units? Wait a second with the units. Hold on. Where this phi naught is equal to h over e. So this thing is called flux quantum. Okay, it's just a unit of flux created by these constants of nature. Okay, and this thing is area. It's basically, if you take the coherence length, it's the area. It's actually twice the area of a circle of the coherence length. Okay, so if you take a radius, of 2 psi, right, then you get exactly this this thing. So we're dividing the flux quantum by this area.
So that's the minimal size for the bubble.
So yeah, what we'll see. Okay, let me just tell you the physics. The physics is that each vortex, if I take a bunch of vortices, each vortex has a core, and the size of the core is of order psi. Okay, so if I have vortices, imagine that I have a vortex of size psi, okay, and I have another vortex of size psi, and I start packing them together. What this is telling me, it's telling me that the flux, and each vortex like this can carry a flux phi naught, which we will see. I didn't show you yet, but basically the flux through each one of these vortices is phi naught. Then you see that when h is equal to hc2, and I want to have okay, let me explain it this way. So imagine that I bring in flux. I bring in fluxes of size phi naught over this area. Okay, the total magnetic field is basically just the number of these vortices. Okay, and the area that these sorry, it's not the total flux is the sum over the flux. Okay, so imagine that my sample size is L by L. Okay, then the magnetic field H is equal to the number of vortices times phi naught divided by L squared. Okay, now if H becomes of order hc2, it means that I need to have the number, okay, so yeah, okay, sorry. So what we can take from this thing is that the distance between vortices, what do I want to say? The distance between vortices is, how can I explain this?
The density.
Yeah, this is like density. This is like density times phi naught, right? This is density times phi naught. So this is the density of vortices, right? So the square root of density Square root of density is the distance between vortices. It's basically this n over L squared. Now, what I want to say is that HC2 is exactly the point where the density becomes 1 over psi. Okay, so it means that the distance between vortices becomes of the order of their healing length. So that's when the vortices, so imagine that when the magnetic field, okay, let me draw it here. So when H is smaller than HC2, then I'm going to have the vortices, basically the distance between them is going to be much larger than psi. And then the density n here, n is equal to n over L, is much larger than psi. But we see that at HC2, the density becomes 1 over psi squared, meaning that the distance between them becomes of order psi. So when H is equal to HC2, and then it means that basically they're overlapping. So it gives us the limit where the vortices start to overlap. Once they start to overlap, you can imagine that the magnetic field basically is so strong that the order parameter doesn't even have time to heal between vortex to vortex. And that kills the superconductor. So that gives you an intuition why this is the critical field. Okay, now what I want to do, how much time do we have? Now I want to talk about HC1. So this was HC2. Remember this expression, okay? This is an important, very important expression. This is the upper critical field for a type 2 superconductor. Now let's do HC1, which is the point where the first vortex penetrates into the sample. How much time do we have, by the way? We have until 5:30 or something?
20 minutes.
20 minutes, okay. Yeah, by the way, I have a meeting, and then we're supposed to go to this outing, so we have to be very strict in time. Yeah, so what we want to do now is let's assume that this is a superconducting sample. Okay? Okay? And I want to assume that there is a single vortex penetrating into the sample. Okay, so magnetic field is penetrating like this. So in this case, G, which is this Gibbs free energy, minus, let's say, minus the superconducting F is just going to be L times epsilon, which I'll explain in a moment, minus the integral over H dot B over 4 pi d3r. Now, this guy is the energy gain of putting this vortex in the sample. Okay? So remember that without the vortex, B is equal to 0, and therefore this term doesn't exist, and G is equal to F. Okay? But there is also an energy gain, an energy loss, sorry, due to the fact that we killed superconductivity inside this vortex core. Okay? So from this we get and what is L? This is L. Okay? And epsilon is the energy per unit length. Now, what is this guy? This guy we can also compute. This is basically, I want to argue that this is h over 4 pi times phi naught times L. Why phi naught? We will see this later. But basically the flux penetrating through this thing is phi naught. So, and the size of this thing I'm going to assume is psi. So, sorry, not psi, L, phi naught, H. Yeah, why don't I have units of length here? Ah, okay, yeah. So, sorry, the region, okay, it actually doesn't matter. So I have a vortex and the total flux through it is phi naught. So I can, instead of this, I can write B and then integrate over this area, but I'm just going to get phi naught. So this gives me, and L is the length. Okay, so this is the, okay, so this is this term. So from here, what I find is that HC1 is basically just given by L and L cancel. So it's 4 pi, it's 4 pi epsilon over phi naught. Okay? So epsilon is the energy per unit length of this, is the energy per unit length. Phi naught is the flux quantum. So this is the energy per unit length. So it's energy, yeah. So, you know, the h squared has units of, so h,
It's energy to volume.
yeah, it's energy. No, epsilon has units of energy per length.
No, but h squared.
Yeah, h squared is energy density. So phi naught has units of
Energy over,
square root of energy. You can work out that this has units of magnetic field. Okay. Okay. So now what we want to do is we want to estimate epsilon. Okay. Now let us estimate epsilon. Okay. So to do that, we remember that kappa is much larger than 1. Okay. Now, why is kappa much larger than 1? Because we're talking about a type 2 superconductor, right? We want to compute HC1. HC1 is a quantity that exists only for a type 2 superconductor. So the kind of configuration we think about is something like this. We have basically, if I plot psi of r, then near the vortex it needs to go to 0, like this. And the magnetic field, right? The magnetic field is basically changing. This is, the length scale here is lambda, and the length scale here is psi, and psi is much smaller than lambda. So we can basically assume that we're basically going to do this in the limit where psi goes to 0. Then we write the equation.
What is the black line? The magnetic field?
The magnetic field, oh sorry, yes.
H?
B of x. No, h is constant.
Okay.
I remind you that h is always constant, always constant. So this is B of r. Okay, so Maxwell's equation which I remind you can be derived from the free energy just by taking a functional derivative with respect to A, gives us 1 over 4 pi grad B is equal to the current, the supercurrent, which is this, grad theta minus E over, okay, EA. Okay. Now to your question, Joseph. Now we've departed from the Landau gauge, from the London gauge. Okay. And the reason we depart from the London gauge is, remember that I told you guys that the London gauge is something that you can apply only if you don't have vortices. Because vortices are basically situations where the gradient of theta has circulation. And these circulation points are things that you cannot remove with a smooth gauge. Okay, I can't make a gauge transformation that will make this disappear. You can also think about it as if it is a London gauge, but I can't get rid of the circulation part of grad of theta.
Why, going a little bit back, when we talked about the phase, the chords, why did we say that? Why did we draw it like we have a minimum? We have a maximum number of chords with minimum flux. Why don't we have chords with?
Yeah, so that comes from flux quantization. So I'm kind of moving too fast. I probably should have. So when we talked about the superfluid, I showed you that there is this basically quantization of circulation. But maybe you're right. Maybe I should pause before I do this. Maybe make a comment. And that's, imagine that we have something like a ring, okay, where here you have B not equal to 0 and here you have B equal to 0, and this is a superconductor. And so we have flux coming through here. So then if you write F, okay, minus F naught, okay, and what I mean by F naught is, let's assume, and I'm looking at F here in this region, okay, then F naught is the condensate without variation, just mu squared over 2V naught, okay. So if I subtract this, what I'm going to get is an integral d dr over the ring area, okay, rho naught over 2m, and then I'm going to have grad theta minus E star A squared plus B squared. Okay, so this is basically dead. That's all you have. Okay, because inside the region B is equal to 0. And yeah, and here we basically okay, so this, let's call this delta F, and here we plug in psi is equal to the square root of rho e to the I theta. That's what we basically do. Okay, and we also demand that the integral, the closed integral A dl, because there is flux, this is not equal to 0. This is equal to some flux, phi. Okay? Yeah. Now, on the other hand, the closed integral over grad theta over a closed loop, right, like this, is equal to 2 pi n. Why is it equal to 2 pi n? Because the wave function needs to be single value.
It's a winding function. Yeah.
What?
Winding number.
It's a winding number, exactly. Okay, so then what you see. So this is basically the reason. Okay, but let me show you. Yeah. So, okay, what does this imply? This implies that delta F becomes equal to rho naught over 2m in integral d dr over something like yeah, we can take out 2 pi here, 2 pi rho naught, and then I have n minus phi over phi naught squared. Now, why is this phi naught squared? Because, again, remember that phi naught is e over 2 pi, basically. Right? Because h bar is equal to 1. So h. This is e star. Okay, so what this tells us is, okay, it doesn't, of course we can put any flux through this ring, but it tells us something about the supercurrent that is a winding. So, yeah. How can I explain this? Let's see. Okay, yeah, so what this implies, what does it imply? Yeah, you're right, I should have prepared an explanation for flux quantization, which is another issue. You know what? Actually, forget about this. No. We're going to actually show. You know what? This is not the direction. This is something. Forget about this. This is not. We can actually show it from the equations. So, no, this was a wrong. This was a red herring. Actually, this from this equation, okay, and the single valuedness of this of the order parameter, okay. Here, by the way, it's the same thing. So in here, we basically assume that psi is equal to square root of rho e to the I theta, and we neglected the variations in rho. Why do we neglect the variations in rho? I've just erased it because they change, you know, over a very small area, which I neglect, and the magnetic field is changing very, very slow. This is B of r, and this is psi of r. So I'm basically only looking at the, so now we'll see exactly why the flux quantization is phi naught. and it has nothing to do with what I just showed. That was a mistake. But the point is that here we still have this quantization condition. Okay? So up to now I didn't show you why the flux is finite. But now what I do is, okay, so let me erase this. So from this equation I move things to the other side. I get lambda squared rotor of B plus A is equal to phi naught over 2 pi times grad theta, just by definition, because E star is phi naught over 2 pi. Okay, and here I've wait a second. Yeah, I've divided by E squared on both sides. Okay? So,
What is lambda?
lambda, okay, lambda is this we defined in the beginning. This is the penetration depth. Okay? Okay, I don't remember the exact expression right now. Okay. Good. So now we can do an integral over both sides. So we get lambda squared, the closed integral over some contour gamma. So I'm going around this thing with some contour gamma. Okay. So I get cross B dl plus the integral ds B, right? So the closed integral over A, I use Stokes' theorem. This thing is equal to phi naught over 2 pi times dl over the same gamma grad theta. Okay? Now, this guy here, you agree with me that this guy is some 2 pi n, right?
Right.
Okay? Now let's take n equal to 1, which is the smallest one. So then I get here phi naught. I get over there. Let me erase this for a moment. Now, okay, now, so now what I get is, now I put all of them under ds integral, and I write lambda squared cross of B plus B minus phi naught delta of R in the z direction. Okay, this is just, and this is delta function in 2 dimensions. Okay.
It's not a ring delta. It's R vector.
It's R. It's the distance from the core. So I assume that this is cylindrical, and this is the distance from the cylindrical coordinate. But now the point is that this equation, you see, it doesn't depend on the contour I chose. So I can take it as small as I want. So, you know, if this is the density, this is like some energy density, then it must hold locally. I can always take it to be so small that nothing is varying, essentially. Except it has to be larger than psi, but psi is 0 for my as far as I'm concerned. And then I get this is equal to that. Okay? And this guy is equal to minus lambda squared Laplacian B. So I get the equation minus lambda Laplacian of b plus b is equal to phi naught delta of r z. So you can think about this as, this is like a differential equation, and this is a source. So you see that the minimal amount of flux that you can penetrate in, there is a minimal amount of source flux, and this is phi naught, and this comes from the quantization of circulation. Okay, this is the origin why it's phi naught.
But it could have been 2 phi naught, 3 phi naught.
Yes, it could have been more. But what we want to see now is the more flux you put in, remember, the larger the energy gain from the magnetic field term is, and then the larger the energy also of the vortex is going to be. So we want the minimal possible flux you can put in, not larger. Okay? Okay, and then basically, okay, so I don't have time, but next time we will start from this equation, and we will see that, you know, in the limit where r is much greater than lambda, and r much smaller than lambda, you can look at different equations. So in the limit r much larger than lambda, you can forget about this delta function because you're far away, it's 0. And then you're just going to get you're going to get that b goes like some b naught e to the minus r over lambda. Okay? And in the other limit, in this limit, you get an equation which looks like lambda squared over phi naught Laplacian b is equal to delta of r. This is basically a Laplacian in 2 dimensions. Now, you know that in 3 dimensions, the Green's function of the Laplacian is 1 over r. But in 2 dimensions, the Green's function of the Laplacian is the log. Okay, so b of r is equal to phi naught over 2 pi lambda squared log of lambda over r. Okay, so that's the solution. So let me quickly, and actually you can solve this equation in the general case. So let me make a box here. In the general case, we have b of r is equal to phi naught over 2 pi lambda squared k naught of r over lambda, where this guy is the Bessel function. Bessel function of the second kind. Okay, so and that's, it means that close it's a log, and far away it decays exponentially. But in the bottom line, okay, and I don't have much time, so let me just sketch it out. In the bottom line, we can now use this to compute the energy density of this thing, okay, and let me just explain. So because the first term is okay, so basically it turns out that the main contribution comes from the vicinity close to the vortex core, and then so we basically plug this in. So yeah, let me erase this. We don't need this anymore. So basically, what we write is that f is equal to the integral over rho naught over 2m grad theta minus e star over E star A plus B squared over 8 pi. Okay, and it turns out that this term contributes much more than this term. F comes out to be L times phi naught squared over 2 pi lambda squared times log of lambda over psi. Okay, and why? Because we integrate, psi is like our lower cutoff that cuts off the log, and lambda is the limit where we move to this solution. So we basically integrate from psi to lambda, and that gives us the following solution, that HC1 is phi naught over 4 pi lambda squared log of lambda over psi. HC is equal to 1 over square root of 2 phi naught over 2 pi lambda psi. I didn't show you this, but if you plug in phi naught, lambda, and psi, then you get exactly the HC that we had. So I remind you that this guy is just the square root of mu squared over, sorry, it's 8 pi, sorry, 8 pi mu squared over V naught. Okay, that's this HC is the same thing. And HC2, I remind you, is phi naught over 2 pi psi squared. So this is the take-home message of today's class, that indeed you see that that in the limit where kappa, I remind you that kappa here is larger than 1 over square root of 2. And in this limit, HC1 is smaller than HC, that is smaller than HC2. So it indeed gives us this picture that we had here. Okay, and the larger kappa is going to be, the larger these guys are going to move away from HC. Okay? Yeah, and sorry for making it such a mess, but this is the price we have to pay for the absence of time. Okay, that's it. מה?
זה אותו דבר כמו שאמרנו בשבוע שעבר, שעל הקלסיאן שאמור להיות גרדיאנט, דיברגנס